A 10-meter tall conical tank is oriented so that the base of the cone is facing upward. If the tank is 12 meters across at the top, find the amount of work necessary to pump water out of the top of the tank if the tank is currently half full. Water has a density of 1,000 kilograms per cubic meter. Okay, so the change in this problem is that the tank here is a different shape than a simple cylinder. So the conical tank, let's sketch one here. It's going to look something like this. All right, now we're told that it's 10 meters tall. So the height of this is 10 meters. It's 12 meters across at the top, so 12 meters this way. And we want to know the amount of work necessary to pump water out of the top of the tank if the tank is currently half full. So the water level is approximately right here, and that's at 5 meters since it's half full. Okay, so let's take a look at what we can do. Now, what we of course need to do is we need to figure out the weight of each slab of water, and that weight is going to be a force because it's the mass of the object times an acceleration, and that acceleration is due to gravity. So the kilogram meter per second squared, that's the definition of a Newton, so that gives me force. Now, if I have to apply a force and move something through a distance, that's the Newton meter, which is the joule, so that's work. So I need to figure out what the weight of each slab here is going to be and how far it has to travel to go outside of the tank. So to do this, I need a few pieces of information. So the work here, as I mentioned, is going to be the integral from the lower level of the water, or whatever fluid it is, to the upper level. And then we're going to take its weight density multiply that by an area of a cross-sectional plane of the fluid at the top, and then that's going to be multiplied by the distance that that plane or slab has to travel in order to exit. And of course, we're orienting dy here, yeah. Now, to get started, we know the density of the fluid. That was given as 1,000 kilograms per cubic meter. All right, but that's not the weight density. The weight density is that kilograms per cubic meter multiplied by the gravitational constant, so 9.8 meters per second squared. So when we multiply, this becomes 9.8 times 1,000 is, of course, 9,800. But then we have kilograms, kilogram meter per second squared, and then that's per cubic meter. Now, I could actually reduce the meter measurement, but I'm not, simply because kilograms meter per second squared is our definition of newtons. So this is newtons per cubic meter, so that's the weight density. All right, now the area of the cross-section. So this is where it can get a little bit tricky based off the shape. In a cylinder, right circular cylinder that is, we have a shape that is pretty straightforward. It's very predictable all the way down. It's circular and it has the same radius all the way through. The issue here is that the top of this is circular, so this disc is circular, but it is changing radius with height. So that's a complication that we have to deal with. So let's try and zoom in on this to understand how to go about this. All right, so I'm going to first cut away to a triangle. Okay, and I'll cut away to this triangle right down here, and I'm not going to reorient it, although I think it actually helps to do so, but I want you to know that I'm using the same triangle. All right, now this same triangle, it has the water level here, okay? And I'm not going to label it as 5 right now. Here's what I'm going to do. I know that this length along the top here, or along the side, is 10 meters, okay? And I know the length along the top is going to be 6 meters because it's 12 meters all the way across the top of the cone, so that's going to be 6. Now this distance here, from here down, I'm going to call that y. That's going to be my current water level. And I know that it's right now at 5, but it's going to drain, and then that's going to become like 4.9, then 4.8, and so forth. So it's still going to change, so I'm going to leave it as a variable. And then also, this distance here, this is, I'm going to call r, the radius. Now, this is a tricky thing for students to see, but geometrically, what we have are 2 triangles. So I have the bigger triangle, which is pink, and I have a smaller triangle, which I'm going to make green. Now, these triangles are similar, and I know they're similar because, number one, they're both right triangles. That's easy enough to tell. But then they also have this exact same angle right here. So they both have that exact same angle because they're on top of each other, which means that this angle has to be the same as this one as well. All right, so that tells me that all 3 angle measures are the same within, so these are similar triangles. And then what's important about similar triangles? Well, the ratio of sides of similar triangles is equal. So for instance, I could take 6 meters divided by r, so the ratio of this side, set that equal to the ratio of the other 2 sides, so 10 over y. I do need to be careful to make sure, the numerator is the bigger triangle both times and the denominator is the smaller triangle both times. Or vice versa, it doesn't really matter as long as I'm consistent. But it's going to give me a way of determining what the value r is, so this radius of the water at any point for the current water level. So for instance, I could say 6y equals 10r, or r equals 6/10 of y, which is of course the same thing as, well, I'll just write it down here, r equals 3/5 of y. Alright, so that gives me a way of determining what the radius of this water level is going to be for any height. Okay? And you should check it for a couple of points just to make sure it works. So if the tank was full, then y would be 10. So 3 times 10 is 30. 30 divided by 5 is 6, so the radius would be 6. Great. When it's at 5, I don't guess we have an answer for that, but we can judge here. So when the water level is at 5, the radius is actually at 3. All right, so it checks out, and that's going to be the radius. Now, when I go to get the area of this disk. That's effectively what I'm working on, is the area of this disk. It's pi times the radius squared. Well, that's going to be pi times 3/5 of y squared. So it's my current water level squared, which would be pi times 9/25 y, or I'll say 9 pi over 25 times y. And I forgot to square my y. Sorry about that. There we go. Okay, so that's the area of this disk. Now keep in mind, ultimately it's volume that I'm interested in, but the width of this disk is dy, and so that's multiplied over here. So area times dy is volume. Okay. Now I need the distance that this thing is going to travel to get out of the tank. So the distance it's going to travel, so the uppermost level of fluid, well, the bottommost level would take 10 meters to get out. At a height of 2, it would take 8 meters to get out. So it's always 10 minus whatever the current water level is. So if the water level is 2, the 2 meter has to go 8 meters to get out. The water level at 6 meters would have to go 4 meters to get out. So 10 minus whatever the water level is. So that the total amount of work to remove this water is going to be the integral from 0 to 5, because that's the current water level, 9,800 times 9 pi over 25 y squared, and 10 minus y dy. And this right here, I'm just going to maybe clean up a little bit. Let's see. I think 9,800 would be divisible by 25. Okay, it is. So I could take that into that and get 392, it looks like. Then I could multiply that by 9, so that's 3528. So I'm going to say this is 3528 times pi times the integral from 0 to 5. I've taken care of all these constants, but I can distribute this constant, or not constant, I can multiply the y squared into these parentheses and make that 10y squared minus y cubed dy, and that looks about as simple as I can get, so I'm going to plug that in to fnint. So 0 to 5, 10x squared minus x cubed dx. All right, there's the value of that integral. That's going to get multiplied by 3528 times pi. So it looks like we get 2,886,338 Newton meters, because we're taking the Newton, which was the volume of each slab through a distance, so Newton meters, which is joules. And there we have it.